couple of interesting things I want to talk about. We're dealing with an integer valued equation, and it's in three variables, x, y, and z. Now, I didn't have any idea how to approach this until I read about something called completing the product on Michael Penn's channel. And that's actually the technique that we employ right here. Now, just a couple of comments. We're not interested in what they call trivial solutions here. For example, the solution 0, 0, 2 zeros, in other words, that says x equals 0, y equals 0, and call it 5. You can put anything here, 5. And you can see that when you substitute 0 in for x, again, this is the x coordinate right here. That's the y coordinate right there. And that's the z coordinate right there. It's easy to verify that when you substitute x equals 0, y equals 0, and z equals 0, you actually get 0. We're not interested in those type of solutions. Those are called trivial solutions, trivial. Okay, let me get that word spelled, trivial, T-R-I-V-I-A-L. Okay, those are trivial solutions. We're interested in just counting the non-trivial solutions, Okay, so again, not interested in the trivials. They comprise actually an infinite number of solutions. We're interested in just a finite set of solutions here. Now, something that's really, really useful here is this notion of completing the product. Notice that what I did from here, from our original equation, all I did was add 3 to both sides. That's called completing the product. Isn't that a miracle? Notice that if you just add 3 to both sides, owing to the presence of this 3 right here, it would be different if there was other numbers in other places. But if you add 3 to both sides, in much the same way you complete the square, you complete the product by making it a factorable expression. Initially this is just 3 terms, right? 3 separate terms. And what are you going to do? Just guess? But now that you have it in a factored form, that creates some structure that makes it easier to solve. Now notice that on the right-hand side we have 3, and basically, y'all, this breaks down into 4 separate cases, which is a little surprising. You can think of 3 as 1 times 3, 3 times 1, and you cannot forget the minus considerations here. So you actually have 4 cases, which makes this not hard but burdensome. It's very onerous to go through all this and do it, but at least you have enough structure to have an algorithm to actually produce the solutions here. Now, let's take a look at just, and you can kind of see what's happening here. Let's just look at this case 1, all right? This means that x minus 1 has to equal to 1. That's what this said. Or that means that this factor here, x minus 1, has to equal 1. What's the only way that can happen is if x is 2, right? And so you can see how many solutions we have with 2. Here's a 2, here's a 2. The 2 is the first coordinate all the way across here. I think we have, what, 8 or something? It's incredible, how much I think this is 8 solutions here. But notice that 2 is the first coordinate. Now, the rest of it is just, you have to make, now what else has to happen? This part here would have to be, come out to be, YZ would have to be equal to 6. You'll see that, folks? The product YZ would have to be equal to 6 in order to give 6 minus 3 is equal to this 3. You see what, it gives you just enough structure, but it's still kind of tedious, all right? And so if you'll take a look at these solutions right here, 2 times 3 is 6, right? Y times Z is 6. 6 minus 3 will give you the 3. And so this necessarily is going to be a solution. But you have to reverse it too. 3 times 2 is 6. Minus 2 times minus 3 is 6. Minus 3 times minus 2. And also you can't forget 1 times 6, 6 times 1 minus 1. It's, you know what I mean? So I mean, it does work out. It does work out. And you can verify that it like we can just do one solution if you want. Let's try maybe this guy right here. Okay, seeing is believing, right? But you know, if you're doing the arithmetic right down here, it has to work out here because of the unique factorizations into the 4 cases. So let's take a look right here, folks. So 2 times -6 times -1, that would be right here. 2 times -6 times -1. Okay, isn't that 12? So I'll put a 12 right there. Again, y'all, what I'm doing is I'm just substituting this. Actually, I should be putting it in up above here, but it'll work out. Okay, so and then also now minus 3 times x would be -6, right? Okay, and then of course y times z is 6. So you see, you get all these minus signs cancel, and you got a minus sign here, so you have -6. And you can see this works, right? This part right here would add up to 0. I should have written it right up here, okay? But this 12 minus 6 sums to 0, and that would make it a solution to this equation right up here, okay? And y'all, you can check all of these others, but it's kind of neat how it works out. Again, this is called completing the product. This little miracle step right here of adding 3 to both sides gives you something that means these 4 terms multiply out and produce a factored state, which we can use in these 4 separate cases. Again, feel free to check some of these others, but I'm pretty sure they're all correct. And let's see right here, I believe we have 1, 2, 3, 4, 5, 6, 7, 8 solutions. Down here, we caught a little bit of a break with 2. We needed a 4 right here, right? We needed a 4 in this position. And that can happen with just -2 times -2, and then 2 times 2, and the rest of it follows, you know. Down here, this was the case that created all the trivial solutions, which I didn't count. And you can verify this. You get these where z and y can just be any integer you want. And then, of course, here's our very last case, which was fairly easy. I don't think I missed anything on that. But in any event, I think we have 8, 6, and 4 solutions here. Unless something tells me I may have left something out down here. But there you go, folks. Hope you enjoyed.